And this is the Waves Homework Booklet question 13. We got figure 1 again showing a side view of a string on a guitar. So string cannot move at either of the two bridges, so it's worth noting that there's a bridge there, we're told it can't move, therefore it must be nodes at that point. When it's vibrating in its first harmonic, the frequency of the sound produced 108 Hz. Sketch the stationary wave produced when the string is vibrating in its first harmonic. What sketch means is draw it as well as you possibly can. It does not mean go in and do something revolting like this. It might have been what sketch meant in your art. It is not what sketch means in physics. Draw it. There's only a single piece of string, so just draw that string as best you can. Let's get rid of that again. And then, so we've got the string. First harmonic means longest possible wavelength, lowest possible frequency. So I've simply got one antinode in the middle. Calculate the wavelength of the first harmonic. Well, the wavelength is twice the length of the string, so it's 2 lots of 0.64 is 1.28 meters. And calculate the speed. We were given the frequency, we got the wavelength, absolute gimme mark. C equals f lambda, multiply the two numbers together. C equals f lambda, multiply the 108 that you were given with the 1.28 that you were given there. There's your answer to two significant figures, 104 meters per second. When tuning the guitarist produces an overtone that's got a node from 0.16 meters. Now, an overtone is a name for a harmonic other than the first harmonic. So it's just a harmonic that actually exists that's higher than the first harmonic. But it's an overtone. It is a harmonic. So it's not the same situation as the violin string in the previous question, in question 11, but it's this idea that we're forcing a higher harmonic, so we're forcing a node at that point. So we've got a node at 0.16, there will be other nodes as well, it turns out. On figure 2, again, it's sketched that, and notice this, label all the nodes that are present. Really important that you read those instructions, follow those carefully. So, if I've got a node there, 0.16, you should recognise that that's a quarter of the way along. So I'm going to have 4 quarters on there. 1, 2, 3, 4, 5 nodes marked. And one of the marks was for having this central node in the middle. So it should be, actually get that out, measure the length of that string, and then split it up into 4, which I didn't do perfectly, but pretty close. So one mark was for having 4 antinodes, the next mark was labelling all the nodes and for having them evenly split, and specifically for having that middle node there in the middle. Asked to calculate the frequency of that overtone. 2 ways you could do this. You could say, well, I've now got 4 antinodes. I know that's going to give me the 4th harmonic, in other words, 4 times the frequency I had before, 432. Or I could look at this and say, well, I've got the same speed I had before, which I worked out back here. Must be the same speed, same must be unit length, same tension. And I've got a new wavelength. My new wavelength is half the length of the string, 0.32 meters. So I could use the speed and the length of the string and get to the same value. Either way, I'm going to get to 430 Hertz. The guitarist needs to raise the frequency of the first harmonic of the string. State one way he could achieve that. The easiest thing would be to say to increase the tension. We've only been asked how we're going to raise it. We've not been asked to say how much it is. But what I'll be looking at is F equals 1 over 2L root T upon mu. That's the frequency of the first harmonic. So I could increase the tension. I could decrease the mu, the mass per unit length. Is it really the same string if I do that? Not sure. I could also decrease the length, would give me a higher frequency. Perhaps the simplest one, increasing the tension. So that's the Waves Homework Booklet question 13.